Great. Today I'm going to be talking about how we do automated bug hunting for IoT devices. So you've seen other talks at this conference about vulnerabilities in embedded devices, IoT, non-IoT, etc. Today there will definitely be bugs, but that'll be at the end, because really what I'm focusing on is how do we automate the process of searching for those. So first of all, we're going to go through the fundamentals of how we can use program analysis techniques to do vulnerability discovery. If I untangle myself. That was dumb. Cool. We'll cover some of the past work in this area, talk about why automation is important, what are some of the challenges in doing it, and how different techniques can help us do that. We'll talk about some of the issues with the existing tools out there and how we can improve those. And then we'll go through 20 vulnerabilities in different, or more than 20 vulnerabilities in 20 different devices as an example of how to use this to discover both bugs that people have found in the past manually, but also new vulnerabilities. As a brief introduction to myself, I am a low-level hardware and RF and firmware hacker. I run Riverloop Security, where we do penetration testing primarily for clients in that space. And I also am, as she said, CEO of Pilot Security, where we make automated tools to help people find issues in IoT firmware. So when we talk about one of these devices, right, the components at risk, you probably all know this, right? We have the hardware, the actual circuit boards. We have the firmware, which is what we're going to be focusing on today. And then we have the back end, where the data backhaul and everything is going. So today we'll focus primarily on firmware because it's the component that's tying this all together. And how do we look at them today, right? So there's different options. You probably have all worked with some of these, right? So first of all, network scanning of devices. I enjoy seeing what Google thinks we all do for a living. So apparently for network scanning, you just put your laptop on top of a box of donuts, and then you find the vulnerabilities. But joking aside, right? So what you could do in this case is we approach it like a network penetration test. We use our standard tools. But this is difficult for embedded. The network services are often unstable. We may not be able to hit the areas of interest, either because they're not exposed by default or because they're over proprietary protocols, whether that's some SCADA protocol, RF protocols, etc. And we are very limited by only looking at the exposed services. By the time we put something together, a big system in a plane fuselage, we do care about each one of those components, but we may not be able to see it from a network perspective, testing from the outside. Another technique we could use is manual firmware analysis. So there's open source tools. Probably some of you have used things like binwalk. Unpack, recover a file system, and then start running techniques to find hard-coded keys, passwords, outdated libraries, configuration files, binaries that then we're going to load into a disassembler or decompiler and do analysis on. But the complexity here very quickly grows. If binwalk works, excellent. If it doesn't, you really need to dig into how the binary formats are working. And there's a lot in the firmware outside of those file systems that you also care about, the bootloaders, SSBL, FSBL. So there's a lot of limitations there. Another technique is to go hands-on, start enumerating different protocols and buses. And we do this all the time on devices, right? You're going to go find the debugging ports, extract data from flash chips, interact with the RF. But at this point, we need the physical devices to do the analysis. And those type of basic low-cost tools that you can get started with very quickly stop working when they're outside the idea of what the designer had originally made. And again, this is only letting us see some different avenues, right? Before we saw network, then we saw from the firmware perspective. From this device, we're just going to see the debug and ports and data memory. And lastly, and I put this on here because I really do not like this approach, if you cannot tell from the graphic. A lot of companies ask their vendors, do you make this securely? The vendor is likely to say yes. Right, and that may not be malicious. It's the person filling out the 200 lines, they don't know. They don't know how the product is working. They aren't thinking like a penetration tester. And lastly, their idea of risk may not align much at all to what you care about in the company that you're testing for or buying the product for. So, I've told you a little bit about why the manual analysis is hampered today in this. Let's talk about how we can use program analysis to find vulnerabilities. Who here has done like automatic program analysis? Just so I have a show of hands. 1, 2, okay, cool. Well, don't worry, it's easy. The good news is firmware has the problems of yesterday, right? We still have stack buffer overflows. It is rare to have exploit mitigations. Constant buffer sizes are happy. There's unchecked boundaries. There are limitless possibilities for exploiters here. We can use indications like vulnerable C functions. We can use indications like externally provided input to start looking for specific bug classes. So how do we do this? I would encourage those who are just getting in program analysis to think about it as decomposing a bug that you want to look for and deconstructing it. And we do this by thinking about 2 operations. What are the reads happening? What are the writes happening here? And reducing the bug that we're looking for to these primitives allow us to abstract it. And then we can use program analysis to try to match against that bug class, the bug pattern. And we typically look for this, at least when we do it, in an intermediate language because we don't want to code to every assembly format. And so we're going to use an intermediate language to look for it. So let's take, for example, the textbook stack buffer overflow, right? How many people have seen this? Hopefully. Right, yeah, exactly. This is straight out. So let's look at how we decompose this. So first of all, we're going to read in an unbounded external input, right? In this case, argv1. We're going to allocate a stack buffer. We consider this a write, an allocation, because it's committing to the stack. So buff 100, right? And then we're going to write the input to the stack, which is our sink. And we simplify the concept, right? Obviously, stir copy itself is not writing that input to the stack. But for simplicity, we encode the understanding of some of these reads and writes into higher level functions like stir copy in this case, to just simplify the analysis. Right? So we have this, then we have this, and then we are successful, right? So I just talked briefly about sources and sinks. Let's touch on that for those of you who haven't looked at those. So when we talk about a source, we're talking about where does the external input in the program come from? Specifically, which, ideally, from an operation that we know an attacker can control, like reading in data from a network. We use this, the sources, to filter out bugs that are unreachable. Then we look at the sinks. Where does that external input get processed or written to memory? And this is what we use to filter out unreachable end vulnerabilities. So we're looking at an operation which we care about, like a vulnerable write here. I do want to give you some references on past work in case you're interested in digging into this more. So this talk's theme, and you'll see this in a moment, was inspired by Exploiteer's talk at DEF CON, where they titled the talk, Hacking 20 Devices in 45 Minutes. I think they were kind enough to give me 45 minutes today, but we're going to spend very little time actually hacking the devices manually because we're going to let the computer do it for us, right? So at the end, we'll go through 20 different devices. We'll show you how it automatically can find bugs in there using some of these techniques I'm talking about. For those people who are interested in reading up on program analysis, These are some papers and references if you want to read into them. Sophia on our team, Sophia Denton, has enough automatic exploit generation, binary rockstar, some great Spirit of 90s is alive in Brooklyn, some good introductory talks to how to use specifically in Binary Ninja and some other tools. And then Sean Heeland and Rolf Rose obviously are awesome in this field. And then there's of tools for doing analysis, right? If we look at the historic landscape, on the left side, we have tools that look at source code. On the right, we have ones that are focused on binary. There's dynamic and static analysis tools. There's human tools like reading the disassembly yourself. And different ones of these bring different strengths to the table, right? Some of you have probably used source code analyzers, dynamic instrumentation and PIN and so forth. But some things that I wanted to talk about briefly is where compilers as program analysis tools hit challenges, right? So if you're working from source code, you can use Clang, go to LLVM. We get a nice intermediate representation in LLVM IR. It has great security checks built in, but it's a compiler, right? For reverse engineers, we need a lifter. We need to look starting from the binaries. There are tools that try to lift to LLVM IR from compiled binaries. These often have large output. We are trying to standardize to compiler types because that's what's in the intermediate representation. But another approach is to lift from the assembly to an intermediate representation that is meant for reverse engineering. We internally use Binary Ninja's intermediate language, MLIL. There's other tools such as Ghidra. Those have some limitations like not having single static assignment form or range analysis by default in them. So let's touch briefly on why automation, right? I talked about how some of you have probably done source code analysis, and this is great for finding things like logic bugs, command injection, etc. But notably in embedded, we have two things that are a bit unique, or maybe more so than in other programs. So first of all, it's fairly common that we have a binary library that we don't have access to even as the developers, right? How many of you have worked with like programming embedded devices and you get a HAL, a hardware abstraction layer from the chip vendor, and you just link against it? Anyone program embedded? All right, cool. Then you're just going to have to trust me. You get given this binary. You need to talk to the hardware. You're not going to write it. Qualcomm, Broadcom, whoever, give you this binary, and you're linking that in. That's now part of your product. You may have vulnerabilities from that. You don't know what the source code is. Your source code analysis is blind to this. So that's the first thing. The second thing is we're going to have a lot of things get compiled out due to optimizations when we're targeting small code size for embedded, especially. And you can also have false positives, as you've probably seen in any product you've used source code analysis on, when it's analyzing dead code that's not actually running. And from a numbers perspective, right, with 15 billion devices by 2022, and probably there's not 1.8 million of us to go fix those in this conference or any conference, we need to find some way to automate this. At least that's my opinion. And specifically so that we can find issues before they cause harm. Even if we had enough of us and we all sat there and we all analyzed every product before it went onto the store shelves, we still want to move that earlier in the process so that we can reduce development costs. We can get more things actually patched before releases. And tools like GitHub are doing this for like web applications, Ruby, Node, etc., where they're looking at dependencies, but it's not that simple in embedded at all. There's also the issue of how are we thorough in large code bases, right? I'm at least not perfect when I get given a flow graph that looks like that. It is very unlikely that at least I am going to look at every branch in this CFG with the same amount of attention and the same attention to detail, no matter how many energy drinks you have. So automation, if we can encode a good check and experts' research methods into this, then automation can apply that same check through the whole CFG, right? So I just told you that automatic analysis is great, but let's talk about some of the challenges in it. So In traditional computation, we have a growing adoption of type-safe languages, not so much in embedded yet. In traditional computation, we have optimized tools for static analysis. In embedded, this is fairly new. We're getting increased processor support thanks to Binja and Ghidra. In traditional compute, we have standardized IDEs that allow integration of source code analysis tools. In embedded, every chip vendor has their own IDE. And lastly, in traditional compute, fuzzing suites are straightforward, or more straightforward. There's good harnessing capabilities. And if somebody asked me in the hardware hacking panel the other day, they asked our panel, how do I do fuzzing in embedded? And I think all of our answer was exactly you did. And I think all of our answer is, this is a challenge due to hardware interrupt handlers and specific layouts requiring instrumentation. So to answer the question, can we apply these security techniques from traditional compute to embedded? Yes, but it's non-trivial to implement. We can't just use the same tools. What we can do is apply the techniques. We can use static analysis to screen for bug classes. We can use emulation to drive some limited fuzzing. We can use satisfiability solving to constrain some variables. And we can integrate into the development life cycle, right? Just like in other ecosystems, when we have our development team go and do a build and go to QA, and we can add security assurance into the automated scans there and feedback security knowledge along with functional bugs. And so at least when I think about this, my objectives in building these type of tools and techniques are how do we let computers find the majority of issues, let all of us focus on solving the hard problems, and try to catch these issues before they cause harm. Okay, let's talk about a few technical challenges. So first of all, how do we encode those read and write primitives? I told you it was very easy in a stack buffer overflow. I lied to you, right? In some of the examples I'll show you of bugs in a moment, there was a function called do system command. Okay, all of us can probably guess what that does, right? This is probably a sync we care about. This is probably system. But a computer doesn't know that, right? Some vendor has made a proprietary wrapper for some reason. And so we need to deal with some of those edge cases. Similarly, from an information flow analysis perspective, if you start looking at a single static assignment form, what I'm showing here is we take a variable, let's say that's attacker controlled, we write it to a register, we do some operation to fill it in with data, and then we access from the memory location again. When we look at this in a disassembler, we can quickly sort this out in our heads, but for a computer to sort that out, it is treating those as different, and seeing the information flow through SNPrintf is a difficult challenge. Similarly, variable range recovery, where you have something called phi nodes in program analysis, where you don't know which parameter is actually feeding into that node in the CFG, right? It could be A1 or A2, those two blocks. By the time we get to that bottom block, we don't know which one ran from a static. We could do symbolic execution on a backwards slice, but that is typically can be very computationally intensive, and we don't want to do that if we don't have to. And then we have these issues where we have these base assumptions like stir copy being a write, but we don't want to give the researcher or the developer false positives. So when the stir copy has a check done right before it, this is probably not how we'd program it, right? Most of us would use stir n copy, but often you see these type of checks that are legitimate guards that make it safe. We have to find this, we have to understand the buffer, we have to understand the limitation, and then we have to say, okay, this bug isn't actually reachable by an attacker. And then I wanted to add some stuff to talk briefly about how do we determine bug relevance, right? So I just talked a little bit about reachability. Can an attacker controllable input get to the bug? Are there guards? Is it on a dead code path? Where does that input come from? But also, it's important to look at exposure. Is the service running? Is it listening if it's running? If it's not listening, is it making outbound connections? Are those done securely? Is this something that we care about doing program analysis on? And for this, we use a number of techniques to actually determine those things, but one of them is emulation, right? Where we're trying to put this file system into an instrumented kernel, watch what happens, watch what comes online from a network perspective, and which services and binaries are running that allow us to decide where to target our effort. Now, as some of these came up in the questions yesterday as well, so I'll touch on it only briefly, but there's a lot of great prior work out there, Avatar 2, Firmidine, FirmFuzz. I think the key thing to take away here is that there's a lot of edge cases when you try to apply these techniques at scale. There's security challenges when you try to run them in a service because you need low-level kernel access for a lot of these tools to work. And we have to work, if we're trying to run at scale, without an expectation of somebody spending time doing custom harnessing. How am I doing on time? Anyone? I can't convert my watch. 30 minutes left? Okay. Sorry, guys. You're still stuck with me. So let's talk briefly about some issues in tool support that we ran into when building this and how we fixed it. Because if anyone's interested in getting into this, I think you will probably run into these and similar and more issues. And I want to explain some of the things we see to arm you on how you might overcome them. So as one example, on MIPS binaries, we were working in Binary Ninja, and it couldn't always find main, and so it wasn't dumping the control flow graph, so the functions weren't being lifted, we weren't getting symbols, and so there were no vulnerabilities. Now, there were probably vulnerabilities, right? So we had to get that untangled. And in this case, it was because of mu-c libc being used, an embedded libc variant. And so we wrote an algorithm to grab the first argument, check if it was a data segment pointer, dereference it, turn it into a function, and then set reanalysis. These type of issues will quickly block your initial analysis and hold you up. Now this one, hopefully you don't run into because we pushed it back publicly to their product. So now the product now implements this algorithm for you, so you don't need to do it. Another one that you saw me talk about earlier is how do we do SSA variables across something like snprintf or sprintf. This is a specific example from one of the binaries that I'll talk about vulnerabilities in a moment, right? So if we follow this along, the attacker controllable input is coming in line 1, right, through that sprintf. But it's going into the single static assignment variable on line 0, R0 pound 1. And so by the time we call system, which is actually on the variable you see on line 2, the computer doesn't know those are the same. They obviously are to us. We see the memory dereference happening. But from a single static assignment perspective, these are not seen as the same variables. So we have to do a lot of work to generically trace across those. Okay. At this point, what I'm going to do is go through 20 different products that we took, downloaded the firmware from the internet, fed them through the automatic analysis pipeline from just the binary off the vendor's webpage, and saw what bugs came out. For a lot of these, I'm going to refer to them using work that other people have found previously. And because it's such a pain to do disclosure on 20 devices, but also because it helps us confirm that the vulnerabilities that the computer found are actually exploitable vulnerabilities in these products. So I'll go through those, and then at the end, I'll release some new vulnerabilities for the last few. Okay, so the first device is this Tenda router. And this is wonderful because I don't know if you can see it there, but I'll zoom in. It has anti-hacking. So I thought, why would we even bother looking at it? I mean, we're not going to find anything. I went on Amazon. It says we have anti-hacking. I'm like, shit, we're done. Okay, well, how it processes HTTP requests is that it has this binary bin HTTPD that gathers the data from the socket, and then it sends it over to this binary called app data center. This app data center is about to be your best friend for the next 5 minutes. This is what parses and uses the data. So Just to orient you, in a lot of these slides, on the right-hand side here, you'll see a screenshot that I've highlighted some things from our automated analysis tool to show you what it's finding. So in this case, it was finding system was called at a specific address, A7C0, and argument 0 was attacker controllable. Let's look at what that actually is. I took this output and then I had to find the toughest part of this slide deck was figuring out which vulnerabilities this actually was and if somebody had ever found these before. So I traced this one back to a CVE from 2017. Don't worry, they didn't patch it. This is like a 2019 firmware version, still vulnerable. And in this case, at this address, system is being called, being passed an attacker-controlled value. When we look at what that actually is, in disassembly, it's a function for handling USB ejection. And I've annotated the disassembly here so that you can follow along. It's taking data off of the server, action, and dev name, seeing if you're supposed to do a deletion of that USB device. And if so, it takes this command parameter, right, CFM post net control, passes in %s, attacker controlled input from up above, and then we call system on it. Excellent, right? Nice and simple, pass directly to system. So in this case, this is an example of what it can find. This was confirmed as somebody had manually found this in the past. All right, let's pick another device. Also from Tenda, looks a little different. I didn't check if this one technically had anti-hacking. But in this case, sprintf had a format string vulnerability, where an attacker could control the input to the format string at this 147BC address, argument 2. Let's look at what that actually looks like. In this case, it ends up being traced down from a log function that the attacker can control input to. And this one didn't have a CVE, but somebody had found it on somebody's random GitHub that they had mentioned it, so they had confirmed it. So now let's switch and look at some stack buffer overflows. Okay, another Tenda device. In this one, it's with stir copy. Now, there's a lot of stir copy, right? But we don't want to look at every single one of those. That is going to be too many false positives. So what we're letting the tool do is filter down all these potentially vulnerable functions to the ones that it actually thinks are exploitable with high likelihood. And in this case, 66DD0 ends up to be a form setting Wi-Fi parameters, in this case, the SSID. Now, I forget, did somebody find this one? Maybe not. I don't know if somebody, maybe I'm accidentally sharing this one. Oh well. So this is the SSID set. I think somebody found a similar one with a different field, but a human is going to find one vulnerability and say, okay, I can set like the password, I get command injection or a buffer overflow. You know, obviously there's a lot of form fields being taken in, and one thing that automated analysis can do is point us to every instance that the developer needs to fix, or see if they actually have fixed all of them. So this ended up hitting every router we looked at from this vendor. It affected it. You know, so obviously all A's, simple buffer overflow. You don't need to do anything fancy here. And we're in. Another device from the same manufacturer, different address. In this case, to my point, this is something to do with the MAC addresses, right? I think it came from a similar input field in the web server. They're reading in the user argument, setting it again, hits every device that we looked at. Again, this one you have to do a few things before you bang A's on your keyboard, but it's still nice and straightforward to get your exploitation with. Okay, I'm sorry, we're really beating up on Tenda right now. One more, I think. Again, in this case, they're setting the time for the NTP server. Same issue, right? So the point and why I'm beating this one a few times is that automated analysis can help us find across a wide range of devices, and also all the different points within those binaries that are actually reachable by this type of bug. So we can make sure they all get fixed. All right, back to command injections. Okay, I guess one more with Tenda. This is a C CGI handler inside HTTPD. They're getting a variable. And let's see, in this case, it's a MAC address coming in that ends up being put into CFM MAC %s. Again, gives us a nice simple command injection. This was found manually by somebody in 2018, but without knowing about that, the automated tooling is just able to find this from looking at the firmware. So your exploitation here is just straightforward, right? Semicolon, telnet D, bind, you get a root telnet shell. Simple enough. Oh, another one, why not? Another one feeding in device name. Okay, so we're going to move on from Tenda because I just really, it was just too easy. So let's look at a D-Link, right? So this has a binary called BOA on it that's running, I believe by default at startup. At this memory address, the automated tooling found system command injection. And when we look at what it is, somebody had found this manually back in 2018, where they're feeding in there's something I think that has to do with logging that ends up getting passed down to this function. I do want to point out that it's not all, automatic analysis of firmware is not all about finding these types of binary exploitation or command injection, right? The simple stuff still matters, right? So looking at, just reducing some of the human effort to find things like, hard-coded passwords or so forth is still important and can help us all do our jobs faster. D-Link has another service called Go-Ahead. For those of you not familiar, Go-Ahead is a web server that I think is well named for exploit developers, right? It is just go ahead. And in this case, it was pretty straightforward. We had a user command input that came and got passed down through a few layers, but eventually ends up being a command injection. Huawei has a UPnP, a universal plug-and-play service running on this router that they have a vulnerable system command injection on. This was found manually by somebody in 2017. The automatic analysis, in this case, it came through XML. The automatic analysis is still able to follow it and find that it's a command injection inside their firmware upgrade packaging here. On an ASUS device, a web server, again, that's running with a command injection. In this case, you have to do a little work. You have to use a pipe instead of a semicolon. Hopefully you guys can follow along. And you have to encode. You have to do entity encoding, very difficult. Again, in this case, we're finding this automatically. Obviously, I've labeled the variables. Disassemblers don't label them user-controlled for you, so I labeled it for the sake of the slides. In this one, it's a ubiquity switch. Instead of system, it's execl in this case. Same effect for the attacker. Let's go back to some stack buffer overflows. Everyone still following along? Are you bored yet of just too many bugs? No? Okay, good. I'm glad. So TP-Link web server, they have stir copy. There's a few that happen when we narrow it down to the ones that actually matter. In this case, they're handling, I believe, a release of an IP address in this case. And there's a stack buffer that's smaller. Let's see, do we allocate it in here? It looks like the allocation is outside this screenshot, but I think it's 0x33, the same thing they're mem setting it to. Attacker-controlled user input longer than that gives us our overflow. ASUS, another stir copy. In this case, they're taking data off of a list, deserializing it. Again, we were able to find this looks like we found automatically the same thing somebody had found in that CVE there. So we know it's actually exploitable and a valid finding. Another ASUS device, sprintf in this case, but it's still a stack buffer overflow that we're actually exploiting. We're not worrying about printf vulnerabilities because it's a hard-coded buffer. of the format string, but we're overflowing the stack buffer because the format string is %s%s, and the attacker controls the input. But if we actually look at some that are format string vulnerabilities, in this case vprintf, the first variable, the format string, is attacker controlled in this case, so we can start to control the stack with things like %ps or whatever you want to inject there. This was a 2019 CVE. Okay. So I just went through a number of ones that we had found automatically without knowledge of CVEs, and then took and figured out, okay, this was a CVE somebody had found, this is a valid finding, etc. And I wanted to share how we can do this automatically without spending the manual time to go sort through these entire things. I wanted to share a few that are new for you as well. So these all have 2020 CVEs. We found them and started just closing them in 2019, but the vendor didn't reply, so whatever, here they are for you. So this is a camera that has a command injection. And if we look at what it is, right, so the automatic analysis found an interprocedural call, an IPC call for processing system command. It gives us a command injection at this address. It's at least available locally. We didn't look to see if it was there was an external exploit chain path for it. So, really the question around the impact does require some more looking to see if you can get in from an external path. If anyone's interested in digging in, there's the memory address to start at, and I'm happy to point you to the right firmware, 95B4, and you can go sort through and see if it's externally available. So we disclosed that in September of 2019. The vendor did not reply, so we're going public with it today. The CV will be posted after I get off stage. Then another one, a DVR recorder. So actually this one we were looking, and we had found a 2013 blog post that we looked at. It's like, oh, this is interesting. Looks like something, I'm sure they patched it, right? It was disclosed in 2013. So we downloaded the latest firmware that said, oh, it has all the security patches in it. And it's still vulnerable. The address is a little different and so forth. It was a 2018 firmware that was supposed to increase at least password security. And if you look at the person who found this in 2013, they used IDA. So this is a screenshot from them on the left. This is the automated analysis on the right. I'm sorry that you probably can't read it. I can barely read it on that screen. But what you may be able to notice is there's comments that have been added, and that's from the automatic tooling, adding comments to the disassembly to show you where it thinks the exploit is and what the risk is. So we started disclosing this September 1st, 2019. After eventually, hopefully getting to the right contact, and never heard back, so disclosing it today. These ones I've obfuscated for the last two devices because the disclosure is still pending. Hard-coded passwords, right? So you guys can all guess that MD5 passwords without salts are probably not great for security on devices when they're hard-coded. And similarly, on this device, there was a previous disclosure by somebody else about file access in the CGI handler. When we ran the automatic analysis, it showed that there's actually command injection as well, so 2-for-1 special. But that's all I have for you guys today in terms of bugs. I'm happy to dive into those more or answer any questions about sort of why program analysis, how the program analysis is working. I don't know how much time we have, but if we run out, I'm happy to talk outside as well. Hopefully you all enjoyed. Thanks for coming.
Thank you, sir. Anyone have questions?
So I have a question, very specific question regarding firmware analysis. So how in few firmwares I have seen that it is taking input or it is validating input on ROM file. It's basically a flash, NAND flash. So when I try to emulate with QEMU, it takes a flash name as a NAND flash or something. NAND QEMU emulated flash or something.
Sorry, I'm having trouble hearing, but I think you were saying you were trying to emulate a firmware in QEMU and you needed data from the NAND flash?
Yeah, exactly. So the NAND flash has some specific name from where it was validating the username or password, something. Like it was validating user input from the flash memory. And in QEMU, I tried my best to name those flash. So is there any way that while emulating the firmwares, you can name the flash drives?
Okay, let's see if I get this right. So you're saying the firmware is reading data off of the NAND flash, and then it's not validating the data it's reading off. So if you could control the value in flash, you could attack it. Is that what you're saying?
No. So what it was reading is like it have some specific name of the flash. For example, ROM file. ROM file was the name of the flash that they have given, from where that binary was calling the name. Means from binary was validating. For example, a password. It was reading from the flash drive. So is there any way that you can emulate the flash drives in QEMU with some specific names instead of NAND emulated flash ones or something?
Yeah, you could. Oh, okay. So it's just validating the name of the flash chip.
Yeah.
Yeah, you could definitely change that in QEMU's hardware emulation layer.
Oh.
Yeah, or use something like Avatar that's going to give you lower level controls. So, but yeah, you can modify QEMU to feed it in with a different value for the name.
Okay, so I'll get in touch with you. And second question is like, is there any way through which we can identify direct user inputs from the binary, not by disassembling each and every piece of code?
Yeah, like figure out from the binary what are the valid user inputs. Is that your question?
Yes.
Yes, typically people use like backwards slice stat solving for that, which takes a fair amount of CPU time, depending on the constraints around the input. So you could do that, or you could do, if you had some idea of what domain you wanted to look in, you could do fuzzing and harness it to start finding it that way. The programmatic analysis way to do it is through stat solving. To go back. Yeah.
So you mentioned that you are using program analysis. So was it a static based or a combination of dynamic, symbolic execution and static?
I'm sorry, the things are pointing towards you guys. So say that one more time.
So you said that you are using program analysis. So is it a combination of static and dynamic?
Okay, yeah, so the question is, we're using program analysis. Do we use a combination of static or dynamic? Yeah, absolutely. So at one point you saw in the slides, I was talking about how like we can use emulation as one of the techniques to inform, right? So we use some dynamic analysis to inform where we should focus in the static analysis. We do some other dynamic analysis as well, but I didn't cover it here.
And the lifter which you are using is binary ninja based.
For the static analysis?
Yeah.
Yeah, we use binary ninja, yep.
And how good is Anger with this for firmware analysis?
Say that again?
How good Anger lifter is? Anger framework.
Anger? How good is Anger at it? I mean, it has broad, Anger you can harness to a lot of architectures, so you can use that, and people have used that in like CTFs and stuff. But I'm not, I don't use Anger a lot, so I don't know any specifics. And
I can see that platform is proprietary.
That's just a graph. No, but yes, it is.
So the most of the vulnerability which you marked for the firmware is a proprietary platform, or is it open source?
The tool that we use to find the vulnerabilities that I shared today?
Yes.
Yeah, no, that's a product that we have. So I gave you some examples of how I gave you some of the content from within it, but the overall system is a product that companies use to do analysis.
And let's say in some cases you find difficult to extract from binwalk. So is there any automated solution for that, or you have to deal with manually?
I'll say that one more time.
So in some cases, if you're dealing with a firmware, you could not extract with binwalk.
Mm-hmm.
So it must be a proprietary format for sure.
Yeah, yeah.
So
There's
do you have automated solution for that, or?
yeah, yeah. So the open source tools like Binwalk are limited in what they can extract, right? And there's a lot of edge cases. So a lot of the time that our team spends is writing custom unpackers for different edge cases, so that the automated tool can unpack a lot more than like Binwalk could.
Okay, thank you.
So most of the vulnerabilities that you've shown here, right, could be caught by static code analysis, right?
Yeah.
Because a
If
lot
you
of command injections, all those things. If we do a combination of static code analysis plus binary scan, we use Black Duck's proprietary tool, Proticode, for doing a scan. So if we combine these two processes, will that be equivalent to the program analysis, what you said, or?
say that again. So you were saying, were you asking about like,
So-
can you combine code analysis with this analysis to?
No, what I'm trying to figure out is like we do static code analysis during development, and once the build is ready, we do a binary scan. Binary analysis using Proticode. So combining this, will that solve the problem? Like what you're explaining, the shortfall of all the static code and dynamic code analysis, right?
It really depends. So a lot of, probably not. Doing the code analysis is good, right? And then doing a second scan after is good as well. But it really depends how your binary analysis is working. If it's not focused on firmware, and if it's not doing deep unpacking, to his question about like how are you unpacking the multiple levels of these firmwares, then a lot of the sort of I don't want to talk about any specific ones. I'm happy to talk after, right? But a lot of you'll hit limitations very quickly on if they can actually find the vulnerabilities or find the data. So you'll have a lot of tools that are really looking for like information disclosure, like a hard-coded password. But obviously that's not all the types of bugs that you find. Happy to talk more though.
Any other have questions?
Great. Thank you guys so much. Hope you have a good rest of the day.